So last time we looked at Q selection problem, right? If you remember. So there's this problem is of underspecification in the data. If there's certain correlation between the bias Q and the task Q, right? Then the model can also choose the bias Q for doing their stuff, right? And that could potentially be a problem when you move out of the training regime. And so to address this, we looked into intentionally biased models because oftentimes it's easier to train a model that is biased than unbiased. And then based on this model, you do kind of different weighting of the training samples to fix this issue for the main model of interest. Okay, so this time we're going to take a look at a different type of domain shift, distribution shift between the training set and the test set. Domain generalization. Actually, we talked a little bit about this domain generalization problem. So what is it? You have multiple domains for model development, right? In this case, you have something called PAX dataset. It has photos, art painting, cartoon, and sketch. So different styles of how the objects are visualized in your visual media. And then you see, let's say the model is exposed to 3 types of domains here. And then the task is to let this model generalize well to the 4th type of image. All the classes are shared. So, for example, you've seen the photo, art painting, cartoon versions of guitar. And then you now want to generalize this to a sketch type. Yeah? Is it possible to learn this kind of model, right? That's the question. I want to, well, that was already simple, but I want to simplify this further. So I want to just say, for development, we have 4 types of images, 2 types of colors, 2 types of shapes. And then at deployment, you have the same types of shapes, but with a totally new color, blue color that you have never seen before. And Y, again, is the task label, and Z is the domain label. Okay. So what people have been doing in this domain is they try to train a representation. Well, first of all, they try to kind of divide a whole model into 2 parts. One is kind of the representation part, and the other one is based on the representation, they train a classifier on top, okay? And their treatment was more focused on the representation part. So the representation is now kind of ignorant or invariant to the changes in the domain. So representation doesn't have any information about domain, but has full information about the task. And then it becomes easier to train a model on top of it. And then the model as a whole will be focusing on the task rather than the domain. And so here the goal again is to make the representation conducive to task classifiers, but free of domain or bias cues. Okay, does it make sense? I prepared some more slides to make sure this is more intuitive. So the first method, I'm going to talk about 2 methods here. So one is a domain adversarial neural network. By the way, the 2 methods that I'm going to introduce today, they don't work in practice actually. People say, yeah, people did some evaluation on top of it and then said, yeah, no, it doesn't work. Why do I talk about it, right, today? Because I find the methods still interesting and potentially useful. So maybe for this problem, it doesn't work, but maybe for the other problems, you may find the technique itself useful. Okay. Right, so let me introduce domain adversarial neural network, first of all. So again, we have input images like that. And then we think about how to, yeah, I'm pausing a bit because you know, when there's noise here, it gets recorded. So sometimes my voice doesn't get become audible. So, okay. So given the input images, your labels are according to the shape. So you have ones and twos according to the shape. And then you have embedding space, which is the representation. Let's say, yeah, this is initialization. So your initial representation will look something like this. Mm-hmm. And then you train both the representation and the classifier according to the task prediction laws, right? Which is the usual training. And then your task, yeah, Y is going to train the representation in this way. So let's say it's kind of sorted now, right? So according to color, you have left and right kind of separation, and according to shape, you have top and bottom separation now. And the decision boundary classifier on top of this representation will look like a horizontal line dividing the triangles and circles, okay? And then we kind of fit these new samples to this model and see what happens, right? I mean, this is just a hypothetical kind of scenario, but let's say it gets kind of broken, it goes weird with these inputs, right? So let's say blue data points are kind of far away from the green and red data points, and there the behavior of the representation is not defined very well. And so maybe if you extend the horizontal kind of decision boundary to that region, it doesn't hold longer that the above part is triangle and the lower part is circle. Okay, and then yeah, the accuracy for these data points are super low. I mean, that's the main worry for the domain adversarial neural network and domain generalization in general. So how do you fix that, right? The problem was that the space was still variant with respect to color. And the aim now is to kind of make the representation invariant to color altogether. Okay. So now, given input images, since we know the domains, right, we are given the domain labels, Z1, Z equals to 1 or Z equals to 2. So now we can also train a domain classifier on top of the representation. Now the labels are bias labels, okay? And then we are training just this classifier on top, which gives you a decision boundary again. And this is a color classifier, and so the decision boundary will be horizontal this time, okay? And now what you do for the representation given this classifier is you train the representation in such a way that the domain classification becomes very hard, okay? What does that mean, right? Domain classification becomes very hard. How can you move things around here? How can you move the data points around in the representation space such that classification of domain, classification of color becomes so hard? Any ideas? Yeah?
I would say that you could put the presentations kind of close to the decision boundary.
Right. Yeah. So that's exactly the next slide. Yeah.
Yeah,
sure.
we put the samples like in that circles together or the circles together or the triangles together.
Exactly. Yeah. Mm-hmm. So if you train with this objective, you get a representation looking like this, right? So your color classifier is still trying to kind of separate these points against each other, but now it becomes very hard, and the loss is always non-zero and very difficult based on this representation. But it does not affect the task classifier because now it's still variant with respect to task. And the hope here is that once you train such a model, such a representation, even for new colors, the representation sort of treats this new case as kind of as the usual. So the model is now, the representation is now blind to anything that looks like color, right? So even if there's a new color, it kind of knows, yeah, maybe I should ignore that. And then puts those data points nearby the other points in the space in the training set. I mean, that's the hope, right? Not saying that that's the way it works. Okay. So this is more kind of technical description of how this is done, right? So you have an input here, then you have feature extractor in the middle, which is going to give you features. You know, features, embeddings, representations. These are kind of exchangeable terminologies. And then you have a classifier on top, which is, yeah, I drew a linear decision boundary, meaning I was assuming you have a linear classifier on top. But you can also have a multiple layers, so you can also have nonlinear classifier on top. Doesn't matter. And here you have a class task label and classification loss on top of that. So together with this classifier head, your feature and classifier are kind of aiming for good task execution. Whereas for the bottom head, the loss is for the domain label or the bias label. And the aim for the parameters in the classifier is for still better classification of the bias label. But for the features, the gradient is reversed, meaning that the loss minimization problem is now loss maximization problem for the first part of the, the representation part of the network. And the aim is to make the representation invariant to domain, okay? So that's, since there's an adversarial kind of interaction between the loss minimization and loss maximization between the representation and classifier, we call this domain adversarial neural network. Yeah, if you want more technical details, we have separate learning rates for the classifier part and the domain classifier part. I mean, that's what this is trying to, yeah, if the previous slide is not precise enough for you, we have this slide as well. Okay, that was the first method. I want to talk about a slightly different method, but similar in spirit. It's called invariant risk minimization. So in the previous case, we tried to make the representation kind of blind to color. But now what we want to do is we want to prepare a representation in such a way that regardless of the domain that you're encountering, your mechanism is identical. What do you mean by mechanism? What I mean by mechanism is the linear classifier. So the same linear classifier will work for any domain. That's kind of the aim here, right? So so you want a representation which is kind of indifferent to the domain. So in whichever domain you're in, the kind of the mechanism, the kind of the function that you're learning on top of this will be kind of independent of the choice of the domain. And if you write down, so in this case, I wrote down the formulation first before giving you intuition, because I want to kind of add to what I just said in a very hand-wavy way. So here the task is to learn the representation phi. And the objective here is to minimize the empirical risk, the cross-entropy loss, basically, for the whole network, right, on each of the domains, okay? So the first part is quite natural, but you have this constraint saying that the W here, the linear classifier, should be identical. should be the optimal classifier for each of the domains, and they should be kind of identical to each other. Okay, so what does that really try to achieve here, right? So again, we have the same situation. We have a set of input images and corresponding task labels, and we train the model. This is the initialization, and let's say if you train it, you have this kind of task decision boundary on the representation space. Okay. And again, yeah, if you feed OOD sample, then we will probably land on some undefined region, and then the relationship is not guaranteed there. Okay, so what IRM is trying to do is you actually train a classifier for different environments separately. So you have a task classifier for green and task classifier for red, and they will, of course, look different because they're trained on different data. And then what you're trying to do is to align these decision boundaries across different environments. This is possible when you have more than one environment in your training data. Okay. If you have just one training domain, then you can't do this, right? You need some multiple of them. Okay, and after training with this IRM objective, what you're going to have is a representation which puts the points in the representation space in a way that for each of the separate domains, you'll have the same optimal linear classifier on top. Okay, so in other words, this single decision boundary is the optimal for all separate environments. And the intuition is that if you have such a invariant classifier, it's likely that even for a new environment, new color, the same rule will apply to this case. Okay, sounds a bit plausible actually, because it's coming from the causal principles, right? So whatever is causal is a mechanism that's consistent across different situations where all kinds of spurious correlations could be different. And the way you can kind of dig out such a relationship is kind of observing multiple environments. And for each environment, you may come up with different hypotheses of what's the real mechanism, right? Some of them will be correct for some environments, some of them probably wrong. And then you're basically taking intersection of the possible mechanisms across different spaces. And then once you take enough intersections here, then the remaining the remainder is probably something that's consistent across multiple environments. And that's probably something that lets you generalize to new situations because the same rule will probably apply there. So that was IRM, and now I'm going to show you the results, not from the respective papers where these methods are proposed, but rather this kind of evaluation paper where they had a more fair evaluation of previous work. And here they show ERM baseline, which is empirical risk minimization baseline, and that's just a plain training of the neural network, the representation and classifier together without any bias label, without anything special. They just train with cross entropy loss for everything. So intuitively, you should get better result than ERM by using bias labels and kind of learning independent mechanism, or by learning a representation which is ignorant of the bias. But the fact is, if you take a look at the average score across different benchmarks, ERM is giving you 67%, whereas other methods are giving sort of similar result, even worse actually than ERM. So that was kind of a big news in the community, right? They've been doing like theoretically correct and conceptually plausible ways of tackling this, but eventually these are empirically worse or similar to the baseline. So I was surprised too, and here are my thoughts, non-examinable. I still think data is pretty important. Data is a very effective way to communicate your needs with the machine. OD generalization methods in general, they are trying to kind of skip this data part and try to kind of still instruct the model what the model should be doing in this OD undefined region. But that seems a little too hard. And also to make this actually work in practice, work in this undefined region in practice, you need a lot of engineering on top. And typically, in my experience, engineering is much more expensive than collecting annotations. So in terms of practicality, I find it more interesting to assume sufficient amount of data. In that sense, I find kind of Q selection problem more interesting because I expect the Q selection problem to persist even in the limit of infinite data, because Q selection problem is arising mostly from the ratio of biased samples and unbiased samples in the training data. So even if you're scraping the whole data from the web, you'll still see the same kind of bias or skew towards some distribution. And unless you change the way you collect the data dramatically, you would still kind of suffer from the same kind of bias during data collection. So yeah, to me, this problem of addressing task ambiguity and Q selection problem is something that's probably going to persist longer than having to address a new situation. Because, like the set of new situations are kind of gradually reducing nowadays with bigger models that have seen so much data. So, okay, so now let's talk about test time adaptation. Why do I talk about that, right? So far, what have we seen? We have seen that OD generalization is generally impossible without really knowing what's going to come up at test time, right? We have just seen that domain generalization is generally impossible as well. That's one end of the story, right? But on the other end of the spectrum, we have fine-tuning, right? Where we have annotated samples from the deployment scenario. So you have label samples from the upstream, right? Whatever your model have seen, right? And then you train this on downstream, a few downstream label samples. And this is, what everyone is doing, I would say, nowadays when they try to apply the model on their problems, right? But people are trying to seek a solution in the middle, right? Because they're still not very happy with the fact that they still need to do annotations on the deployment scenario. Maybe the distribution is always shifting, so maybe it's super costly to kind of track all the changes in deployment, and whenever there is a big change, they have to re-annotate the samples and so on. So that's understandable. So here, again, the aim is to find out how to assure a good performance, as in fine-tuning, but still use a bit less resources than before. Okay, so there's something called test time adaptation, and it's also called source-free domain adaptation. And the schema, the setting looks like this. So you have some development stage where you train a model on whatever task, right? Like you can think of that as a pre-trained model, like BERT models or GPT models or ImageNet pre-trained models. And then you deploy this model basically, but you're continuously adapting this model to the deployment scenario by using the unlabeled samples from this kind of streaming samples from the deployment for adapting your model further. So this is gaining quite some attention nowadays, since 2020 or something, because this holds so much promise in kind of practicality. You just need to download some model, right, from the web, and then just throw this model somewhere and with this code for adapting the model automatically. And then the model is kind of doing its job pretty well. Why do you call this source-free, by the way? Because there are also other methods that require your pre-trained model to have been pre-trained in a specific way in order to be adaptable at test time, and we call them non-source-free or kind of the methodologies that require source data to adapt to new situations. Source-free here means you can just take whatever model from the web, and then you don't care about how this model is trained. Regardless of that, you can adapt this model to new situations using unlabeled data. That's what source-free here means. That allows model developers to choose more diverse set of models. Yeah, gives more freedom for the model developers. So this is quite interesting. So let's take a look at maybe two most promising or most popular baselines from this domain. Okay, it's an active area of research, so you'll probably find a lot more sophisticated, complex methodologies in this domain. But to cover the most basic stuff, do you know what entropy is? Do you all know what entropy is? Okay. Good. So, do you know, okay, so one-hot vector versus a uniform, okay, let's say there's one-hot vector, yeah, in one-hot vector with all zeros and just 1, 1. And then there's a uniform vector with 1/n for all the entries. Which one has the higher entropy? Yeah. Yeah, okay. So you know it. So when we try to minimize the entropy, what that means is we are trying to make sure that it looks more like a one-hot vector rather than kind of spread across. The scores are spread across, okay? And this paper, 10th paper, found that the OD-ness of the sample is highly correlated with the degree of entropy for each sample in the model prediction. So as you can see here, when the entropy is higher, that means the error is also higher, meaning that the chance of making mistake is higher. At the same time, these are originally the in-distribution data, and noise blur, digital weather, these are kind of different types of OD data. And if you move on to this OD regime, you're going to see higher entropy. So that's kind of, yeah, if you're OD, then you'll see higher entropy. And they try to kind of convert this statement and try to intervene on the entropy part. And yeah, their hypothesis is if they regularize the entropy, then to be smaller, then these points will probably be behaving more like in distribution. Yeah? In other words, the model adapts better to these samples. Okay. So, but the caveat is, let's say you have a single test sample and you tune some of the parameters of the model for minimizing the entropy for that sample. And the obvious optimal solution here is to maximize the, just make it a one-hot vector. Yeah. But then that's not interesting, right? Because it's so easy to just tune the network to just be super confident. Yeah. So it's not a good solution. What they do is, instead of minimizing the entropy for a single sample, they take a batch of samples from the test set, let's say 128 samples, and then they minimize the overall average entropy for all these samples. Then since the ground truths are all different, you can't just make the model commit to one answer. Yeah, and we can avoid the trivial solution in this case. Very simple trick. And the other question is which parameter to optimize. Yeah. So since you don't want to change the model too much according to each of the test batch that the model is going to encounter, and also because you want to make sure the optimization is simple enough. Instead of training the full parameter set for the model, they just train the batch norm parameters, the scale and translation parameter, gamma and beta. By the way, batch norm looks like this, right? So for each batch, for each activation, you're first of all kind of normalizing the activations according to the mean, the batch mean and standard deviation first. And then they're applying some artificial mean and standard deviation with gamma and beta, where gamma and beta are kind of, in this case, learnable. Okay. So that was one method. There's another method that's also quite popular. So it's called Memo, and they were not so happy with Tent because Tent requires a whole batch of test samples. So you know, when there are a lot of users for a service, right, then it's easy to kind of batch all the requests. Like you can wait for 128 requests in a second maybe, and then pass them through this Tent algorithm easily. But let's say you just came up with this tool and there are not so many users, right? Then you can't just wait for 128 requests, right? So it's important that you are more nimble and kind of moving quickly. So they came up with a way to kind of still adapt to a single sample at test time without having to kind of make the model committing to a single solution. The method is simple. Given a single test sample, they do m different augmentations of the same sample, and then they have a batch now, right? Then based on this batch, they minimize the entropy for the overall entropy of the batch. And that kind of has a similar effect as in Tent. That's the argument. Okay, so do people use these technologies? Yeah. I personally haven't seen much use cases. Maybe I'm wrong. Maybe some companies are using this on a daily basis. But here, one thing that we should keep in mind is that there are some extra costs involved, right? So otherwise they just need to come with a training code for training the model and deploy it. That's it, right? But now during the deployment, the model has to kind of still adapt to the new distributions, and that requires a bit of engineering. And also there's always this recurring cost in terms of computation time for adapting the parameters to new samples. And that's gonna, I don't know, make factors more slower for your inference time. So, and then for me personally, I kind of lack confidence that this will continue to work for a longer time horizon, right? Because let's say the model is kind of continuously adapting to new situations, and maybe that drifts your model away from the original way too much. And unless I have a kind of a monitoring system for checking how well the model is still doing in this new situation, I would find it hard to trust and just deploy this model. Well, that's my personal opinion. And then the next thought for me is, okay, to monitor this, I need to annotate a few samples in the new deployment environment. And then we're back again in the situation where we have a few label samples from the deployment scenario. And then the natural choice for me then is to fine-tune the system. So we still have the same kind of situation here. So that's my personal thought on this. And then I wish to move on to adversarial attacks now. So we were talking about OD generalization. And why do we talk about adversarial attacks, right? How are they related? Mm-hmm. Any thoughts on this? Okay. So OD generalization means the distribution kind of shifts, right? So I thought about this for quite some time, and I think there are many explanations why and how we can describe adversarial situation as an out of distribution. One could think of kind of an adversary who's kind of introducing the hardest environment for you, right? So instead of saying you have photo, art, and cartoonish photos, and then you have sketch, yeah, that's kind of prefixed. You know, someone is fixing the task for you, um, or you're tackling some fixed problem. But now let's say you have trained on some data, and then your environment could be either A, B, or C, right? And then we can assume that there's an adversary whoever that is, they're picking the hardest case among A, B, and C. And that I would say is kind of adversarial situation. And that kind of gives you kind of worst case performance of your model in out of distribution case. So that's one possibility. The other one is, when there's an adversary user, right? Adversarial user, the user can just do whatever they want to do, and they can always move away from the training training situation. So in that sense, you're also kind of introducing out of distribution changes in the environment. Yeah. So, sure.
What do you mean by the user is going away from the
Yeah. So one example is actually here. It's called Dark AI Forum, where they come with different ways to kind of break down systems or kind of do bad things, right, using AI or against AI. Jailbreaking is one possibility, right? So those companies who are providing services for AI chatbot or and so on, right? They try to um, come up with a system which is resilient to attempts to misalign the model and make the model kind of generate statements which are not nice, right? And for doing that, they are introducing a lot of training data. They're training the system to kind of not go outside the boundary, kind of still be within the okay kind of behavior. But now users can come up with a new kind of new types of data, which are clearly OD, which induces some undefined behavior, right? So the model doesn't know what to do with these inputs because the model has not seen such an input before. And then the model then decides to behave in a weird way, like exposing some of the training data, for example, or exposing some of the not so nice content that's potentially within the training data. So these are kind of examples based on LLMs that we see these days, where people voluntarily look into kind of OD regime to kind of manipulate the model behavior. I hope that answers the question. Okay. So adversarial attacks has been there for quite some time, actually. Since 2014, 15, there has been a surge in the number of papers here. And then it was kind of plateauing since 2021, 2022. But then actually with the ChatGPT in early 2023, late 2022, it started to go up again. Because now with the large language models, there are actually more practical threats that people are coming up with adversarial attacks. So the adversarial attack community is getting very excited about this new revival of their community. Yeah, And companies are getting very much interested in possibilities here, and possibilities to, yeah, of course, defend against these attacks. Yeah, yeah. Adversarial researchers are kind of weird. So I wish to talk a little bit about the setup. What do people do in adversarial attacks, right? Okay, I'll take a break in 5 minutes. Formulation. So when it comes to adversarial generalization and adversarial attacks, um, it's important to remember there are some factors. Yeah. When someone comes with an adversarial setting, you always have to ask these 3 questions. One is, what is the goal of the adversary? Yeah. It's sometimes not so clear. And 2 is, what is the strategy space? What is the action space for the adversary? And 3 is, what kind of knowledge does the adversary have? These are 3 important factors. And then based on these, the goal, strategy, and knowledge, the adversary will probably pick the worst environment for the model. Okay. So there are 2 players in this game. You can also think of this as a game theoretical situation, 2-player game. The devil will pick the worst environment for you, and as model or model developer, your task is still to do the best job. Yeah? What's the advantage of this way of thinking, right? Yeah, of course, there are actual adversarial users. That's one motivation for thinking in this way. But the other one is you can think of the strategy space for the adversary as the set of possible environments that the adversary can come up with. And the adversary in this case is kind of fictitious. All you want to do is to get some kind of worst case guarantee for your model. Yeah. So we kind of know, we don't know exactly what environment this model will be deployed to, but we kind of know the set of possible environments. And we want to make sure that the model is still doing well, even in the worst case scenario within this set of environments. And then you can kind of resort to this kind of adversarial machine learning. So yeah, and then I'm going to cover some basic attacks in this domain. I'll start with FGSM, which is probably the first attack that came up in this area. So I'm going to tell you the goal, strategy space, and knowledge. The goal for the adversary is to attack a classification system in such a way that the classifier is making a wrong prediction for an input, a single input. So let's say this is a panda image, and you want to introduce some strategy here to make the model predict something else for that image. And here, the strategy space is a small perturbation around the input. And typically, in adversarial machine learning, in computer vision domain, they define a LP ball, a small kind of ball in the Euclidean space of inputs as perturbation, additive perturbation. Yeah, so they're going to add something like this, right? And this is a magnified image. So eventually, what you're adding here is something very close to 0 throughout. So it's not perceptible. It's bounded by the maximal value, pixel value throughout the image. So in other words, it's an L infinity norm constraint on the input, on the perturbation. You do that because you want to make sure that the semantics of the image does not change, right? So if the semantics changed, right, then there's no surprise, right? If the actual content of the image changes, then maybe the model reaction should change as well. What is surprising is that even with such a small change, the model behaves differently. And now, also what is important is the knowledge of the attacker. The attacker can basically generate a gradient of the model with respect to the input. So that means the attacker should be able to do gradient, so backpropagation through the model, should be able to feed this input in and should be able to compute the gradient for the input. It's called white box attack because now the attacker knows the model inside out. The attack looks like this. So it's going to introduce a small additive perturbation on top of the image, where the size of the attack is modulated, controlled with this epsilon. And the term here is basically a gradient on top of the input, the gradient of the loss with respect to input. And you're basically adding the gradient, meaning that you're kind of taking a direction in the input space, a small step that is going to maximize the loss, that is going to locally maximize the loss. Okay. The reason why you're taking sine function, by the way, the sine function is kind of substituting for every element in the vector. If it's positive, then you put +1. When it's negative, you put -1, right? The reason you're doing this is because the gradients are typically very noisy, and you want to kind of minimize the noise in the attack, right? And then you're taking sine function, and that kind of enforces your gradient size of the gradient to be kind of within the range of -1 to 1. Then you're taking the multiplication with epsilon here, and that as a whole makes the size of the perturbation within the L epsilon ball in L infinity norm. Okay, so that turns out to work pretty well. Yeah, I'll probably finish the PGD part and then take a break. Okay, so now the PGD attack is an acronym for projected gradient descent. FGSM was just taking a single step in the, you can think of this as an optimization, right? Where the objective is to maximize the loss value. And FGSM was kind of taking a single step in the optimization, in the gradient ascent. Now PGD is taking multiple steps of gradient ascent. Again, the goal is to, reduce classification accuracy, which means you want to increase the loss value. So it's a loss maximization problem within the space of additive perturbations defined by LP norm. So in this case, we go a little bit more general than L infinity, where P could be, of course, infinity, as well as L1 or L2. We can also choose non-conventional p-values like 3 or something, but no one cares about that. So again, now the knowledge here for the adversary is white box. So the adversary can kind of query the model multiple times for the gradient. So now let's take a look at how the algorithm looks like. So the PhD is kind of taking multiple steps, and step at t looks like this. So you have the original image. No, not the original image. The perturbed image at t. Okay. And then you're adding a small perturbation, which looks exactly like the FGSM attack before, right? You take the sine of the gradient, then you're multiplying with the alpha value, which is different from epsilon, right? You're still trying to bound this by epsilon ball, but since we are taking multiple steps, we don't need to kind of restrict the step sizes to epsilon, right? We can also take very small steps, like 1,000 times, and still be within the epsilon ball based on the projection that we're going to apply on top. So on every iteration, we are kind of taking the FGSM step, right? But we always make sure that the perturbed vector is still within the LP vol around the original input by doing projection. So this pi, based on the ball around X node, which is the original image, where the ball is kind of according to the LP norm and the size epsilon, right? So this is the projection. And that's why it's called projected gradient descent. Yeah, maybe you should call this gradient ascent, but the convention is you call this gradient descent for some reason. So comparing the two, you know, the optimization problem, even if you are kind of working on this optimization in the input space, it's a non-convex problem, as in the neural network training for the model parameter. So there's no guarantee of optimality in this, even in this small LP ball. Yeah, so it's important to choose the right optimization. So FGSM and PhD, they can be seen as kind of different optimization schemes. And of course, if you're just taking a single step, then there's much less granularity in how well you're exploring the non-convex landscape. And so PhD oftentimes give you much better result than FGSM. But of course, since you have to take multiple steps, it's more expensive. It depends on how many steps you're taking. So previously, we looked into FGSM and PhD as basic attacks. They assume white box attack on the model, which is great. Makes things a lot easier. Oh well, before white box attack, I want to talk about LP ball around basically the strategy space. We looked into small additive perturbations for the attackers. But is that kind of the end of the story, right? Is that kind of covering all possible perturbations on the image that is not changing the semantics and perhaps not perceptible to humans? Yeah, and I'm giving you another example of perturbation of the input, which is not changing the semantics or visual perception of the input, which is shifting everything to one pixel to the right or left and so on, which is clearly different from LP ball, right? Because, for example, if you measure the L2 distance between the two images, when you add this kind of additive noise, let's say the L2 distance is 10, but if you move everything by a single pixel, I would say the perceptual change is even smaller than introducing noise here. But the L2 distance, where you kind of subtract pixel-wise and then measure the sum of the squares, that's going to be much greater. So does LP ball make sense? And should we take a look at other types of strategy spaces, right? That's kind of the question that people had in adversarial attack domain. And that's also something that, in my personal opinion, led to kind of the decrease in or plateauing of the community. So let's take a kind of a more sober look at kind of what kind of attack scenarios we may encounter with a vision model. So the typical situation that people come up with is a self-driving car and a stop sign, right? The most scariest thing that you can think of regarding stop sign is there's stop sign, but somehow the self-driving car misreads it and then accelerates there, right? So that's the typical example, and that's pretty well-defined classification task, right? You're just given a sign, and you need to classify whether that's a stop sign or something else. But then if you think about the full pipeline between the object in the real world and the model's prediction, we first have a sensor stage, actually. There's camera. And then after this, the pixels are captured. You have a digital image. And actually, in practice, there will be a lot of kind of steps in between, like some normalization of the image and some kind of resizing, cropping, all kinds of steps in between. And then there's model, and then there'll be prediction. So far, we have been kind of looking into the situation where the PGD adversary is kind of tapping into the model input right before the model is applied on top of the raw RGB values of the input. But then the question is that really realistic in practice, right? Because all of that is happening within the software inside a self-driving car. Who can actually come into that software and maybe even just basic security of not letting someone into the car will solve the problem, right? So yeah, and like I was using this adversary with this DALI generated image last year, and I was trying to change this to a new improved version with GPT 4.0, but I forgot to do that for these slides. Let's take a look at a different scenario. So maybe someone could be uploading. So the recognition is not happening in the real world as a self-driving car, but for some reason, there's some user image uploaded to Google Photos or, I don't know, Facebook or Instagram. And the adversary comes in and say, yeah, I want this image to be recognized as something else, right, for some reason. Even in that case, the adversary has to kind of come into the cloud and kind of tap into the stream between the loading of the registration of the image to the memory, and on top of that, the adversary has to add some perturbation there to make this work. I mean, the point is, it's probably not super realistic. So what others have come with is kind of looking at other strategy spaces than additive perturbation, like putting small stickers on stop signs. So if you put these kind of white and black patches on a stop sign according to the right configuration, then these are known to kind of make the self-driving systems misread the sign and maybe accelerate or something. Or you can also use that for kind of avoiding surveillance systems, right? Some of you are probably against the surveillance, automatized kind of tracking of individuals in different cities, right? And the government knowing, yeah, this person has been to this city on this day, and right? So one solution to that is, because we don't know what government is doing with all this data, one solution is we can carry around this kind of poster in front of you, or maybe behind you as well, and that lets you avoid any automatic detection of general humans. So that's one case where the attack is actually not just making harms, but actually helping your privacy, which is interesting. But these are kind of new types of attacks that people looked into. They are called physical attacks. So I'm just pointing to the fact that people is probably unrealistic, and yeah, people realize that as well. So in that sense, the adversary is now kind of tapping into the object in the real world as well, and still working in that in those cases. The other factor that's a little bit unrealistic is that even if you're kind of tackling the real world pipeline, real world object recognition pipeline, you still need to know the internal details of the model, like the model weights and yeah, basically all kinds of details, like even how the samples are normalized and how the samples are quantized and so on, in order to generate these kind of attacks, PGD attack and so on. So that leads us to another type of attack, black box attacks. And I'm slightly more excited about black box attacks than white box attacks in general. So what is black box and what is white box? White box means you basically know whatever you want to know about the model. You have your model.py file on your local machine, and you have the checkpoints, weights, and so on. A black box typically means you don't know all of these, but you have input-output access to the model. You can kind of query some inputs to the model, and you can get some outputs from the model. Of course, there are some limitations, like how many times per minute you can query the model. Yeah, the usual rate limit for APIs. Or if you craft something super weird, then maybe the API recognizes, yeah, this user is weird, and maybe blocks the user from using the system anymore. Or there can be different versions of outputs, different types of outputs the model can give out. So for example, one instance of, later slide, but one instance of that was ChatGPT, right? And you know, GPT-3 used to, Da Vinci models, for example, they used to give you kind of top K probability values. But nowadays, I think they stopped doing that because these details are giving out too much details about the potentially the input data as well, like the training data for the model, and some internal details of the model. So they just give you kind of the final prediction then. Yeah. So depending on the security concern related to the model, those service providers can kind of control the degree of openness of their model outputs. Okay. So what can you do if you have input-output access to a model, right? One typical thing people can do is they give the model a lot of inputs and observe a lot of outputs, and that itself gives you a data set to train a new model on. Yeah, because you know how you train your model, right? You just give a bunch of input-output pairs to the model to train a model. And this is kind of different from giving a bunch of input ground truth pairs, because if you record the input-output pairs from a model, then you're recording all kinds of mistakes the model is making as well. And this pattern of mistakes and confidence values, if these are available as well, then this will kind of instruct this new model that you're training how to mimic the behavior of this target model. And the assumption is, if you train such a model locally, you can basically attack this model. It's called substitute model. And the attacks on this substitute model will probably work for this target model that is black box as well. Because now the substitute model is kind of a mimic, like avatar of the target. So that's one method. The other method is super costly and super dumb, which is, you know, there's another way to get the gradient from a model, which is different from backpropagation. Backpropagation is a very sophisticated, efficient way to get gradient. You know how gradient is defined, right? It's a limit of the differences, model output differences, as the input differences get smaller, right? So let's say it's a 50, so 224 by 224 image, well, times 3 as well for RGB channels. Then you can change each of the pixel value slightly and observe the model outputs based on your pixel changes. If you do that, so 224 by 224 is something like 50,000. If you multiply 3 with that, you get like 150,000 values. And if you do all these forward passes and backward pass, well, just forward passes, and observe how the model reaction changes according to that, then you will get a full gradient vector for the input. Okay, this way you can do PhD again or FGSM as well, but it's very costly, right? You have to call the API like 150 1,000 times. But there are people who kind of developed this idea and came up with a way to do it more efficiently, like sampling from the pixels that are potentially going to be more important. So I'm just mentioning this is another possibility when you have black box access to a model. So one black box machine learning service example is GPT-4, of course. Yeah. Okay, so that was black box attack. But there are some people who say even black box is a bit too much. Is there a way to kind of attack a model that's not known and we don't have access to the inputs and outputs, right? So that's one way to say a no box attack. The other way to say that is you can prepare some attack based on some local models. But you want to now apply this attack on a totally different model and hope that it works. That's another example of transfer attack because now you have not seen any input-output pairs from this model yet. Okay, so that is another possibility. In this case, your target model is F again, and local model is G. And the nice thing is, yeah, for the local model, you have all kinds of axes. Yeah, I already said that, right? You have target model, and for your local model, you're generating an attack, and you're hoping that it generalizes. But there are also quite some degrees of knowledge you have about the target model. Yeah, so if you know, for example, if the target model is GPT-4 or some kind of LLM, then obviously you won't have a ResNet or kind of a vision model on your local machine to attack, yeah, make an attack, right? So even that knowledge that it's a language model is giving you some direction, yeah, some guidance on what kind of model you should be preparing in your local machine. So that corresponds to task, for example. And you know that maybe the GPT is using transformer architecture, right? It's better if you know how many layers there are, right? Then you can prepare some even similar model architecture on your local machine. And if it's even more likely that you'll make a successful attack if the target model, if the training data for the target model is known. Actually, this is a quite strong information that you can give to adversary. And it's kind of understandable that these companies, model providers, are not releasing fully what kind of data that they have trained on, because that's going to increase the level of yeah, attack efficiency, for example, of the attacks. So yeah, so there can be degrees of knowledge on the training data as well. Like if you know the rough information, like roughly from which kind of data they have trained the model on. If they actually have the actual samples, then that's a totally new, a different story, right? That's even even stronger than having black box access. If you know the exact training data, then you can replicate the model even more closely. So yeah, no box attack does not mean it's always weaker than black box attacks. Sometimes based on the knowledge you have, you may have stronger attack than black box cases. So here a critical trick that people have explored is ensembling. So when you're trying to attack a target F, instead of crafting a attack based on a single local model, you can make a attack which is attacking several local models. Because it's again like taking intersection of the solutions, right? As in our IRM, right? In IRM, you're trying to kind of make the representation as a kind of an intersection of all possible environments. But in this case, you can make an attack which is working for all the models. And then it's likely that this attack will also apply to a new target, yeah? So, so this is the original kind of objective for attacking a white box model. You maximize the loss with respect to these constraints. But now when you have a set of local models to attack, then what you do is you maximize your attack, try to maximize the loss for all the models in your local machine at the same time. Let's say there are m models, then you're summing over the loss values of m and try to attack them at the same time. Okay, in this way you can generalize your PGD or your FGSM to work against a lot of models in your local machine. Yeah, that's how you do it, right? So instead of just taking a sine function of the single gradient, you accumulate the gradients from for all the models in your local machine, and then take the sine function afterwards. Yeah, in PhD as well, you're basically replacing any gradient that you have in your algorithm with the summation of the gradients over all the models. So I like to share some kind of intuition here about generalization. Because here it's kind of a new type of generalization. Because in machine learning, when you talk about generalization, it's typically about generalizing to new samples. You have trained on some training set, and then you want to generalize to new samples, right? But here, it's again another type of learning problem. But here, what you're trying to generalize against is the models. You're training your attack on a set of models, and you're hoping to generalize, hoping that this attack generalizes to a new model, right? So I like to draw some parallel between machine learning and transfer attack. So in machine learning, the task is the optimization is basically minimizing your loss function over multiple training samples. You're basically trying to find a solution which is in the intersection of all solutions that make sense for individual data points. Does make sense? Yeah. And then if you do that, then the hope is that even if you have a new test sample, your loss will still be low. And for transfer attack, what you're optimizing is different. Now you're optimizing the input perturbation, delta. But the rest of the objective is quite similar. You're trying to manipulate or optimize the loss value, but you're trying to maximize it this time. And you're trying to maximize it over multiple models instead of multiple samples. So now it's, you're originally optimizing for the parameters for multiple samples, but now you are trying to optimize a single sample over multiple parameters. So it's kind of a dual situation. You have some usual constraints for attacks like this. And now the hope is that for a new model, your loss is still high. Yeah, so I find it quite interesting that attack is kind of giving you a different view on the generalization problem. So yeah, I said it all, right? Objective is minimization versus maximization. Parameter used to be model parameters, but now it's input. Training data used to be samples, but now it's parameters. Possible distribution shift. So there is also distribution shift, right? So if we can prepare a set of models that are close to the target model, then we can make it almost like an in-distribution generalization. But if we don't have information about the target model sufficiently, then there may be some distributional gap between the model here and our set of models. And that poses some difficulty in generalization potentially. Yeah, so as in sample generalization, information about the deployment scenario matters a lot. Yeah, so if you know any information about the target model, then that makes the transfer attack much more effective. Okay, so now we've been talking about kind of, even so far, we always assume there is a single input, and we are generating an attack for this single input. Yeah, but that's quite, inefficient, because generating an attack is very costly, and if you have to generate an attack anew for every sample, then that's very inefficient. So as an adversary, it would be interesting if there's a universal attack, which means you can generate a single attack, and that can be applied to multiple samples. So for vision model, this can take a form of an additive perturbation. And once you add this perturbation on any input, it will induce some misbehavior or some wrong behavior of the vision model. For language models, this can take the form of suffix or prefix. So you can come up with a single suffix or prefix, and whenever you attach this suffix or prefix on some prompt, then it's going to induce some weird behaviors of the model. So these are, so here's one example of universal adversarial attack. Regardless of what kind of image and what kind of semantic category the image has, once you add this image, you will see changes in the model outputs. So it works in practice. Right. That's how it works, right? You can notice that still the perturbation here is depending on the model. So it's not transferable attack, it's very target specific attack, but it's generalizing across images. So here again, you have different directions of generalization. Well, I'll talk briefly about attacking black box language models, and maybe we can talk about the exact algorithm for attacking the language models next time. Okay. Attacking language models. So we need to understand language models first before attacking it. So language model, you used ChatGPT before, right? Or language models in general. You can ask for interesting stuff like how to write a guide for manipulating 2024 election. Yeah, it's too late for manipulation yet. Tell me how to build a bomb. Yeah, or how can I commit text fraud? Provide a tutorial to dispose of a dead body. So they can be very informative for a certain type of people, right? And they can't really ask around, right? They can't even maybe Google search, I don't know. Maybe that's a bit risky. And so they come to ChatGPT and so on and ask for this information. It's quite likely, right? And then usually the language model is supposed to say, no, I can't answer that, right? Because they're all safeguards against it. But here, what the adversary is trying to do is they can attach some adversarial prompt as a suffix at the end of the prompt, and then and then the model suddenly thinks, yeah, maybe I should answer this question, and starts answering, and then answer like, yeah, here's step-by-step plan to destroy humanity. Here's a step-by-step plan to destroy humanity, 1, 2, 3, and so on. Okay, so for this, we need to understand a bit how the structure of LLMs look like. Basically, a language model has a tokenizer as the first step, right? So it takes kind of a character string, the string of characters, and then it goes through a tokenizer, and then it becomes a sequence of tokens, where tokens are basically indices in the vocabulary. So it's kind of when my comes in, right, then it recognizes that, yeah, this part of the sentence where it's my, correspond to token number 120, well, 12 and 79, 12, 79. And then that's the token index. And your sentence will basically look like a sequence of these indices. And then there's an embedding. So you turn these indices into a vector embedding first. And then now it's ready for application of transformer, because neural networks typically require a continuous input to do whatever it wants to do, right? It's a continuous model with that should be trained with gradient. And then you have a transformer on top of that, and then you have a string output for the next token. It will basically output a probability vector across all the possible vocabulary. And then you can take argmax, for example, within this token indices to infer what should be the next token. And then if you turn this token index into a string, then you will have name. Yeah, okay. So, and then that's one iteration in the autoregressive generation. So it's an autoregressive generator. So when you input my, then it goes through the transformer and then predicts the next token name, right? And then you iteratively feed in the, attach the output from the model to the original context, and then feed this again to the model, and then this will generate the next token. And then you attach this next token back to the training input context, and then give it to the model and iterates. This way you can make the model generate sequence of tokens indefinitely. Right, so that's how LLMs work. Of course, there should be some end of sequence or something like some special token to make sure that the LLM stop generating at some point. So input to the language model usually have 3 parts. So one is system prompt, and the other one is user prompt, and the other one is partial predicted text, which is what I explained just before. So system prompt is something that you cannot control as a user. I mean, or sometimes you can also control it depending on what kind of language model provider you're using. And it typically says, you're a helpful assistant, blah, blah, right? And that tends to help the LLM generate answers in the way that the model providers like it to answer. And then you can ask, user prompt is what you give to the model, and then the partial predicted text is some intermediate predictions from the model, and that's attached back to the input. So sequentially, you're generating, sure, the capital of Luxembourg is blah blah. It's very important that the LLMs are aligned, right? Because otherwise, it can give away kind of safety critical information. It can also expose some of the training data, which can be quite serious. Toxic languages, harmful knowledge, lack of empathy, explicit content. So how do people align LLMs to human values? It's called alignment, and that's a big field in LLM technology nowadays. Solution 1 is system prompt. Here's possible system prompt. It's very lengthy, right? You're helpful, respectful, honest assistant, always answer helpfully, blah, blah. A stronger solution is always alignment fine-tuning or alignment training adaptation for the language models. So people use reinforcement learning, human feedback. For ChatGPT, they used it. And this is basically based on some data-based, data-centric tuning. So they can give some of the examples where the model can emulate on treat as exemplars. And then that tends to help with alignment of models. So without alignment, the model tends to say, yeah, align a plan to steal from a charity or non-profit organization, and then it answers truthfully to that. But after the alignment, it says, I'm sorry, I can't assist with that. So that's how it works. And the aim that we have now is called prompt injection attack. So adversary is injecting some of the tokens in the prompt to induce the desired behavior. And even without any like sophisticated algorithm, people have came up with different ways of doing that. So there's some website called Jailbreak Chat, and they came up with different like strategies to make the models be truthful when they are asked harmful questions. Typical examples include like ignore all the instructions that you got before. So that's kind of nullifying the system prompt. And then it typically comes with a hypothetical situation. Yeah, this is I'm preparing a class teaching material, right, about word, peace, and so on. And now we want to show the danger of coming up with a kind of a destroying scheme for humanity. And so we need some bad example here. So please, can you give me some example of a bad actor here? And then the model kind of agrees, yeah, that's an important problem. And then I'll give you all details. And what I'm going to talk about next time is how to kind of algorithmically generate such a suffix. By the way, nowadays, OpenAI and all the language model providers are kind of have come up with a patch against these kind of attacks. So it's not as easy to come up with these suffix anymore, but it used to be possible in the early days. Okay, I'll stop here today, and let's resume next week.